That is a database. and publish on Dandy, and then how to access data on the archive and analyze it. I'm going to go over a no-code approach, graphical user interface that you can download and use to convert and upload data. Then Alberto is going to go over our programming tools, and then I'll take over and show you how to actually analyze data. So we'll try to do a quick tutorial of all of this. So I'm here at this website, nwb-guide.readthedocs. Come on. .io. All right. This stands for NWB Graphical User Interface for Data Entry. So to install this, we just have this installation page. You can pick the installation that matches your operating system. I've already downloaded it and installed it, but it's as simple as just downloading this and going through normal installation steps. Okay, and then once we have that installed, I'm going to go to tutorials, and I'll go to, first you want to generate an example data set. So here we're generating some, I'm just going to delete this pipeline. We're going to generate some data that we can use to demonstrate this conversion. So you go to settings, and then I'm going to delete this and then just press generate. And this will just take a minute or two to generate a few sessions of SpikeGLX and Phi data. So this would be kind of standard output of a NeuroPixel experiment, plus the spike sorting, processing, and manual curation step. These would be the most common formats that we would usually see. We support, again, over 40 different formats. We just wanted to pick one that was fairly common in the field that we've really optimized this for. Yeah.
This new chip, what's called OpenFS?
Mm-hmm.
Is this part of?
It's also supported, yeah. And so with NeuroPixels, you can either record in SpikeGLX format, or you can record with the OpenFS system into their custom binary format, and we support both, conversion of both. We just see that more often we just see this format. That's why we included it. But the other one is equally supported. Yeah. All right. Okay. So now we've created this demo data set. It's here. All right. Now let's go through this tutorial. We're going to walk through converting a single session. So the first thing I'll do is navigate to the Convert tab, and then say Create New Conversion. Test Conversion is the name of the project. We name it so you can save it and come back to it later if you want to. And with that, I'll just click Next. So now we're at the project setup page. Here you can enter in metadata about this. Now, this is the time zone that your data is in, not the time zone that you are in, though it defaults to the time zone that I am in, so it automatically defaulted to Mexico City. But if you collected this data somewhere else, you can enter in another place. For subject ID, I'm just going to say 001, session ID 001. Do I want to publish data on Dandy? I'm going to click no for now. We're going to show that later. And then, okay, so then I can click next. And
so sorry. So yep. This is very important for me, at least for the beginning. So you can convert all your data in this NWB format and not upload it in your platform for a while, at least.
You can, yeah, they're
once
files.
You have, whatever, papers or something.
Yeah, and I would encourage doing that because that will allow you to build your analysis pipelines upon NWB, right? And then when you share the data, you can also share your analysis pipelines.
Right.
Yeah.
So, okay.
And also these NWB files, they use a special compression, a lossless compression algorithm that actually these files tend to be quite a bit smaller than your source data files.
Fantastic.
So it's just a nice bonus.
Including videos, right? I mean,
so this videos is tricky because so videos specifically of like natural behavior. I was talking about the MP4 format earlier. They use a codec that's very good. And so generally, specifically with videos, we suggests to store those outside the NWB files, just link to them. Okay, so I'm gonna pick the SpikeGLX recording interface and the PHY interface. So this is telling the guide what data formats I'm gonna wanna look for. And then I click next. Scroll down. Okay, so now I need to tell it where this data is. So I'll click here. Now, where is my data? You know what? Let me go back to okay, it's in NWB guide testing data. All right, so I made a note there. So I'll go to this. I'll date on. Testing data, single session data. And here I'm loading data for PHY. So I'll click this. This tells it where the source PHY data is. And then I'll do the same for SpikeGLX. I'll just single session, SpikeGLX. For this one, you have to navigate specifically to the data stream that you want to convert. And it tells you here, okay, this one wants the folder, and this one wants like ap.bin or lf.bin. Okay, so I can click next. All right, now what it's done is it's gone into those files and it's extracted as much metadata as it can. And you'll see things like, okay, here's the session start time that it was able to extract from this from these files. And it has a lot of other metadata that's not essential, but it may be recommended. So the color scheme here is yellow, means there's missing metadata, but it's not going to block you from moving forward. But red means it is going to block you because this is data that's required by NWB or Dandy that it wasn't able to find in the source files. So specifically, we need the sex of the subject, we need the species. I'm just going to say this is a mouse, and it needs the age. So I'll put P25W. This is using the ISO 8601 duration format, so this means a period of 25 weeks. Alternatively, you could provide the date of birth. That will also work. Okay, so with that, we can see we're yellow, green, green. By the way, this tab, it's like a lot of very specific metadata about electrophysiology that most of it was able to extract from the source files or just kind of infer. But you can change this if there are specific metadata that you want to include. And I'll just say the institute is UNAM. Let's do that just for fun.
So the original data you uploaded is like in any sort of format? So this is trying to read.
So this is taking data that's stored locally on my computer and converting it to NWB so that I can upload it to Dandy.
And that data was, for example, an Excel sheet?
The data is what would come out of the NeuroPixel standard, like the most common standard NeuroPixel acquisition system. So that's like SpikeGLX data is like voltage over time data in binary format, not in Excel.
Can I ask another question? Mm-hmm. So for example, if you're using different electrodes with different configurations, so these can extract those configurations and
so
map those.
It depends. If you're going to do something really complicated, maybe you can use this with like, you could just set up multiple interfaces with multiple different like formats or maybe even the same format. If you're getting too complicated, you might have to use the programming tools that Alberto will talk about next. Okay. It just kind of depends on the use case and the very specific details.
Okay.
Okay, so here I'm converting. It's running NWB Inspector, which is a separate tool that we have that can inspect NWB files for best practices. So the NWB Inspector actually can work even on files that were created outside of Guide. Any NWB file you can plug into the inspector. We have it as part of this workflow. So it says, these are all yellow, which means they're just warnings, they're not errors. Okay, this experimenter is missing. The experiment description is missing. There's no keywords. We didn't describe the subject. For one of the columns, we have for description, we have the string no description, which is we've detected as a placeholder. We recommend you actually describe it. So there are a few of these, but there's nothing that's going to block us. So let's just proceed on. So then this loads this into NeuroSift. NeuroSift can be used to visualize data on Dandy. It can also be used to visualize local data. So this is loading NeuroSift specifically on the data that we just converted, and then we can use those tools to inspect it and make sure that it looks like we expect. Now this is fake generated data, so it's going to look like junk, but if you have real data, hopefully it'll look like you expect. And then with that, you can do run conversion. So this will actually output NWB files. And then there you go. And if you click this link, it will open up in your directory the NWB file that you just created. And it's as simple as that. Now, it's as simple as that if we support the data types that you want to convert, and if there's no other information you want to add. Now, there often is other information you want to add, in particular like trials tables. Like we didn't say anything in this about any of the tasks that were going on. So we have tutorials to show you how to do that. This is example code for how you read it in Python. We also have MATLAB tutorials that show you how to read this file and append, like hopefully it's just, we've done the heavy lifting at this point. We've taken all of the large raw data. We have ways of reading it in piecewise. So even if that data is huge, it's not going to overload RAM. We package it using lossless compression. And we write it with all of the necessary metadata. So that's all been automated for you, but there often are still a few manual steps, usually with respect to like structured behavioral tasks that you would want to annotate yourself. So we have tutorials for that. But this is generally how the step-by-step for how you would convert raw data. We also have a tutorial here that I'm going to skip over in the interest of time for doing multiple sessions at the same time. Really the only difference here is instead of specifying a specific location for files, you would specify a path pattern that describes how you can find files. So you would say like, oh, here's the path, but instead of having a specific subject, you would say, here's where the subject ID would go. And instead of having a specific session ID, you would say, here's where the session ID would go. And then NWB guide will find all files that match that path pattern and automatically convert all of them for you. If we have time, I can go over that, but I want to make sure that we have enough time for the other stuff. In particular, data publication. So let me just go over that. So here, so you can do this as part of the convert pipeline. If in the beginning you said you wanted to upload to Dandy, but the cool thing about this, we separated it out because even if you didn't use the guide to convert your data, you can use the guide to upload it because it's a really nice interface for uploading data. So here I'm going to first of all, what you would need to do is set your API keys. I've already done this. To get your API keys, it's pretty simple, but you do need to register for Dandy first. So once you have an account on Dandy, you can click your user icon here. This is an API key, which I will change in a minute. But you would just copy this. I mean, I guess it doesn't show the whole thing, but anyway. You would copy this and then paste it into here. There's also another usage mode here, which is staging. So there's a kind of a mirror archive, which is just used for data that's like it's not real data. It's just used for like testing purposes. So if you look at these, a lot of them will just like say test if it loads. Okay, yeah, neurocomp testing workshop data, a data set, a great Dandy set. Yeah, so these are all just like people working through tutorials. Because before we had this, people were uploading lots of test data sets into the archive, and that just wasn't great. So this is a separate archive that has its own API key that you would access the exact same way. And then you can input your main API key and your development API key, which is the one from staging. And you would just submit that. Now, you can either use this dropdown. Once it has your API keys, it can find all Dandy sets that you own. Now, most of you probably won't own any Dandy sets, but if you do, it'll allow you to upload to an existing Dandy set that you own, or you can create a new Dandy set, which I'll do here, and I'll set it to the development server so that I'm not creating a test Dandy set somewhere that I don't want to. Unum test, and then I'll set my license. I will not choose embargo, though you could choose embargo, but then you need to indicate what your award number is. All right, I'll create that. So now it's selected Unum test, and I can upload files. I need to select the file first. Conversions, test conversion. All right, here's the NWB file we just created. And now I've lost Unum, but I can find it again, and I can upload it.
So it's just one NWB file at a time, or
no, you can select the whole directory if you want to.
Fine.
Yeah.
But in one file, you can have a whole experiment.
One session.
Ah, just one session.
Generally one session. You technically could have a whole experiment, but we organize it by session. And
So-
Dandy expects you to organize it by session.
So, and in this case, a session is one day with one specific recording site.
Yeah, like exactly how to define session is tricky because it kind of depends.
Right, depends on the
experiment
experiment.
specific. It's often one day of recording from one subject. I've seen sometimes cases where you could really make a case for there being two sessions in a single day. If you just have two recording sessions that are not related to each other. And then it kind of gets tricky when you have experiments where there's like a training session that's immediately followed by a testing session. It's like, is that one session or is that two sessions? I usually think of that as one session, but it depends. And then it also gets tricky if you have data sets that just are continuous. It's like, well, we recorded for 2 weeks.
Yeah.
It's like, is that one session? Like technically, I guess, but sometimes it's easier to separate by day.
Right.
So you need to upload session by session?
No, you can select the whole directory. I just only had one for the
Okay.
test.
Then can I ask you, well, this is uploading. So for example, we record, deep areas like the basal ganglia. And then for each of the recording sites, we have fMRI, well, an MRI structural,
Yeah.
position. You can incorporate this kind
Yeah,
of thing.
you could incorporate that. It gets a little tricky because there's a separate archive for neuroimaging, but the line gets kind of blurred, right? Like you have primarily a neurophysiology experiment, but you have a component of it that's neuroimaging. So do you submit in two archives or one? I think if you can turn that into like a volumetric image, we would happily accept that in NWB on Dandy, but we don't have automatic tools for that. So you'd have to find your own way to get that in, or you could just, talk with us and we can show you. If you can load that data into MATLAB or Python, we can show you how to use existing neurodata types to get that into an NWB file.
Okay.
Okay, so this was uploaded. You get a link to the page. I think if I refresh this, you'll also see it. Yep, non-test. You can also click this link, which takes you to the DandySet landing page of the data set that we just uploaded, just one file, 18 megabytes. It lists me already as a contributor, which I can edit. And it is currently probably computing the asset summary that it's extracting. Okay, files. Here's the data that we just uploaded. You can open it in NeuroSIF just as you did before. You can also edit the metadata here. So in general, you would maybe put a link to protocols IO page, look at the study target. You can change the license if you want to, enter keywords. The dataset contributors is where you would edit or add contributors. I'll change my name. You can add an item. If you say person, you can enter all of their information. And here you'd add often the similar contributors list to the authors of the paper, though sometimes a bit different for various reasons. There's also metadata for the subject matter, so you can say it's about this disorder or this anatomical feature or genetic type. You can put information about the ethics approval, the protocol identifier, related resources. This is where you would link formally to a paper that's corresponding to this data set, or to a notebook that you've shared on the Dandy Hub that demonstrates how to read and analyze the data set. And then you can link data sets together in projects. Okay. So that's basically how you would convert and upload data. Any questions on that so far? Any more questions?
Any questions to the YouTube?
Okay, great. Alberto, are you ready?
In fact, yeah, I mean, so each NWB file will be a session.
Right.
And then how do you pack all the sessions?
Yeah, so Dandy has a structure that we will follow,
Okay.
which is that, I mean, I'll just show you what it looks like on a real data set, on the actual archive, not the staging. So if I just look at public data sets, I'll just open up one. Okay, this is 75 files, so I'll look at the files. The first level is subject, and then you get your subject ID, and then the second level is sessions. And this is, we call it BIDS flavored. So there's another data standard called BIDS, which specifies the naming conventions for these files and the organization of these files. And so we use something very similar to that.
So, and then for do a proper analysis on all these sessions, how do you pack them to run a MATLAB script?
Yeah. Well, if you're doing it in MATLAB, then you'd want to download it
regression
first.
On all this,
yeah,
charge rate of net.
That's gonna depend a lot on how you want to do it, right? Because if you're doing regression on multiple sessions, like how do you handle intersession differences, right? If you just want to ignore intersession differences and just try regression just on its own, yeah, I mean, what you'd want to do, I guess, is just download all of the data. So the way you can do that is download. So we have an efficient command here, dandy download, and we show you how to install this. So you do pip install command. This will install the dandy command line library, and then you run dandy download, and this command will download the entire data set. Or you can, if you want to look at a single file, you can just go into the file explorer and just click download for one of these. So you can just do that, and it will download this individual file.
But that will be the whole thing.
That's the one session, right? Now, I mentioned that you can read just specific data, and you can, the tools for doing that in MATLAB are just not really very good right now. So in Python, it's much easier to stream data. So I'm going to go over that at the end. The last session, I'm going to talk about how to read data in from the archive to analyze it.
Okay. Thank you.
All right, Alberto, I think you're up.
Yeah. So somebody asked because that screen requesting an NIH number appear for the embargo data set, where that's required for embargo.
Yeah. But if we don't have an NWB,
You can include
which is the
a
case.
reward number that's not NIH there.
Right, how does that work?
Right.
another clean.
Well, that part you can put.
Right. Yeah, well, I like looking technological. Is that working? Yeah, that seems to be working. Pretty good. Okay. So let me do presenter mode here and remember where it is. Slideshow. Okay. So as Ben was mentioning, now the goal of this second session is talking about data conversion. And we have a gradient of tools that allow you to work with less code, less programming effort on your side, but have less flexibility. I'm Ben discussing great detail the guide, which is no coding at all. You see, like you can select if we support the format. If it is a very common format in neuroscience, then you don't need to do a lot of work. I'm gonna start talking about NeuroCom, which is kind of on the middle of the way. And finally, I will talk about PyNWB and NWB, which are the low-level tools that will allow you to have a lot of flexibility. And my goal is to give you an idea. So if I have this type of problem, what tool will I use? And tomorrow we can give you a specific example and sit down with you to solve an issue at a deeper level. Okay, so to recap a little bit, what Ben was mentioning at the beginning is that, okay, so having all the data in NWB is great, and it's great that everybody that knows the format will know where the data is. But actually, converting the diversity of data in neuroscience to the format is quite a big effort. And it is a big effort for many reasons. Among them, there is many formats. There is many formats for electrophysiology. Ugo already mentioned, for example, OpenEFIS versus PyGLX. Even if they can use the same probe, there is a different acquisition system. We have different streams. Like you might be doing behavior and electrophysiology. There are experiments with patch clamp. There are experiments with optical physiology. You may have a structural imaging, etc. And we need to combine them. That's like another source of complexity to the task. The data is large, so sometimes it's not really feasible for you to load everything into RAM. You either need a big machine or sophisticated computing equipment that allow you to write the data a chunk at a time. And finally, it is knowing the format on itself. The format, as Ben mentioned, at the heart is a set of requirements, but there is still flexibility. And within that flexibility, you can do better or worse. So it is good to know the best practices, and we have codified some of the best practices in the tools that we have built to help the community achieve that goal. So NeuroCom was one of the first efforts that Bent started, I think like 5-6 years ago. When did you start NeuroCom? And the goal was this. So we have these formats that are this conversion from formats that are very popular. We want to make it as easy as possible for you. This is a short list of the formats that we support at the time. So on the left side, you have extracellular electrophysiology. Here we have OpenEFIS, as we mentioned before, Ugo was asking. We have BlackRock, European data format. We have SpyGLX, SpyGadgets, BlackRock. We support different common outputs of the sorting algorithms that are most popular out there. KiloSort, Phi, which is used for manual curation, Plexon. We support as well ABF for intracellular electrophysiology. And we support a bunch of other formats for natural behavior like video, audio, video, meaning, any common media containers, such as MP4, MBT, etc., etc. So if your format is in that list, then we can make it very easy for you to do the conversion. This will be supported both in the guide and in NeuroCom library. And Ben would show you this slide before, so just to reiterate, this is how the code at the NeuroCom level looks like. And basically what would you get is first you will have to choose a specific converter from the list that I showed you before. So you go for your converter, you import it, you tell it where the data is, which is what Ben was doing in the guide with clicks, but here we will do it by writing the specific path. You load some metadata that may be missing, and you run that command. So this is the workflow that is equivalent to what Ben was explaining to you with the guide. So let me jump a little bit just to show you and how this looks. So like, this is the conversion gallery that we have in the documentation. This is probably where you first stop, should be, if you have some programming tasks that you want to do at this level. So you come here, and then you look, oh, I want to transform something, and I'm going to run with Hugo example about OpenIFIS. So, okay, I have OpenIFIS. So how will I transform this data? So you click here. It will give you first instructions on how to install the programming library that you require to do it. And then it will give you like code snippet that will tell you, first, you will need to change these for your specific part of your data in your local system. Again, you will load some metadata. You will tell you where do you want the file to be written, and basically you run that. And combining modalities, we have some example as well in the, go ahead. Correct.
We'll have you know, because normally what we have is for each day of recording, you have you know, a subdirectory, and then all of these subdirectories are within one subdirectory. You could click on that one and integrate all of the sessions, or you need to, you know, manually go and do session by session.
Right. So these, all the conversion gallery at this level is session oriented. In this FOSSI definition of session that we have, like an experimental unit of analysis, let's say, to aggregate over a couple of sessions. Let's say you do like 1 month of recordings and you have them structured somewhere in your, with some format in your system. We don't have something as automatic as that. Reason being that the way that you store your folders in your system is very ad hoc and very specific to each lab. Like some labs follow a convention of organizing by date. There is the conversion of organizing by subject that Ben mentioned earlier. Some people just make their own thing, like some super technicality, like getting a hash or something. And we cannot really automate that. We do provide some tools that I can show you that will allow you to basically do that programmatically to some degree. So you can find this tool here that basically you will pass a format of how you usually organize your data and will allow you to iterate over that structure. But that's one more degree of complexity.
Right.
Yeah, so we provide help, but we cannot automate it for that reason. And to answer concretely again, yeah, this is session-based. And I was going to mention that, for example, when you want to combine some, these are like common experimental setups. So for example, electrophysiology and behavior. And you can come to this snippet and it will tell you, so for example, here people combine one BlackRock recording with Sleep, which is a program that does pulse estimation. Like you get the skeleton of an animal in a video as it changes across time. And some sorting over there, like the output of kilo sorting. And if you want to combine these 3 modalities in an NWB file, again for a session, you can do it with this type of logic. All right, so this is how the conversion gallery looks like. This is the type of code that we have in Eurocom to help you convert files easily.
So sorry to interrupt this.
As much as you want.
So I will go again with you know, where we are supposed to be recording. You know, I mean, normally what you do is you can have recordings where you have acute recordings. Every day you're changing where you're recording. And then you need to keep track of where is that. every day in a format that can be also very idiosyncratic. Or you can have electrodes that go deep, as I told you. We use a software that is called Cicerone that is planned to define an electrode trajectory within the brain.
Right.
And then you have a predicted location of where you were recording. That's especially very useful for deep structures. And then again, we keep that on track of that on a very, it's a very idiosyncratic manual way. So for us, it will be very nice to have, that integrated in this database so that when you would like to analyze how the physiology changes the function of anatomy,
Correct.
you have that. You have that information. You can just let's focus on the anterior part of the recordings or the middle ones, and then have this type of things. So I'm wondering whether you have this ability or not.
Right. Yeah, that's a great point, and something that we have been actually working very recently, especially Ben, who spearhead this since the last year. And there are basically two levels to it. So I say first, when you store extracellular electrophysiological data from NWB, one of the pieces of metadata that we store is the probe that you have. And if the geometry of the probe is available, we store it. That's great at the beginning because it allows people to do things like kilosort requires the geometry of the spike sorting to actually be carried out successfully. So that's one step. Then as you were mentioning, you have stereotactical coordinates. We don't have a lot of source formats that actually provide that. We have been working on a standard for precisely storing the different coordinates that people use to plan the surgery. And finally, you have the type of location that you get by doing a post-mortem experiment of where the electrode actually ended up.
Oh, yeah.
And you may want to have that localization. At the moment, we don't have something automatic that will allow you to do this in a super easy way, but we already have the structure in place. And we're currently working with the tool developer. So we'll love to talk about the tool that you're using to make it more streamlined and easier for people to get this data on the format. Because as you mentioned, it's crucial. There are times where we want to go back and analyze some data that is already in the archive and see where the electrode is and where it ended up, because that opens a lot of possibilities for super interesting analysis, right?
Absolutely.
Cool. So yeah, I show you what type of conversion you can do with Neurocom, which again, you will do this when you want to do things a little bit programmatically. And I'm just gonna talk briefly about the features that allow us to do this. So the first thing that Neurocom does is that we have put a lot of work into parsing the metadata from source files. Source files here means the format that your acquisition system outputs. Like for example, OpenIFIS throws some specific files like an XML, JSON, .dat, if that's what you're using. And we ensure that they end up in the right part of the NWB structure. So when you store extracellular electrophysiology, as I was mentioning earlier, NWB creates one of these structures, which is the electrode table. Here you have information about the geometry for neuropixels probe, intersample shift, because not all samples are taken actually at the same time, and the shape of the electrode, etc. And we have put a lot of work on getting all the varieties of the formats and how they change. So basically, you don't have to worry about that. That's a big part of what Neurocom does under the hood.
So sorry, another question. So in the case of the probe geometry, so imagine that you have a session with I don't know what we call Muzaki 64 neural nexus probe. So you have already the geometry of these generic electrodes. In the case of non-generic electrodes, the ones that you design, you have a geometry that is deep, for your lab. Is there an easy way of uploading this, probe geometry into the program?
Right. So Ben was mentioning earlier in an answer to you that we work very closely. I'm a maintainer of the library called Spike Interface, and a sister project, which is basically tries to take care of spike sorting at many levels. And a sister project of that library is one project which is called Probe Interface. And basically what we do there is we have a library of the most common probes available out there. And that just gives you the geometry of the probe and a lot of characteristics of it. Then, on top of that, you need to know the wiring of the probe to the acquisition system, right? Some of them already come recommended by the manufacturer, and we have a way for you to load that very easily, like a couple of lines.
Okay.
But if you did an ad hoc manual wiring, basically we can get a map of that in a format that we have, and we'll allow you to load it. But we don't have that in Neurocom. That's probably something that we should add a tutorial on how to do. If somebody do a manual wiring, how they will get that into Neurocom and therefore into NWB. So
yeah, because now there is a real humongous variety of geometries, electrodes, and some of them are custom and some of them are very standard. So yeah, in fact, this is something that we do in lab. We use different types of electrodes.
I think that you have been going more recently through the library event. Do you remember, for example, where I can showcase some of those wirings? Is that here?
Well, I mean, you have some abilities.
Yeah, we can take a look on this later. I would like to showcase this to you because we are always looking to improve anyway. Yeah, so that's the wiring, which is an important piece of metadata. And what I wanted to mention as well is how Neurocom simplifies these. I mentioned to you that we have these three tiers of converter tools. Guide, which is just clicking like a normal program. Neurocom, which is sort of low code. And we have PyNWB and MatNWB at the end, which is the most low level. And what I want to showcase in this slide is how the equivalent code will look like if you were to use PyNWB. So basically, we are doing all of these for you under the hood without you needing to parse the metadata file or fill out a lot of the things manually. As we mentioned, and you are very well aware, data is becoming larger. NeuroPixels, for example, if you're using, or any volumetric imaging that you might use with a 2-photon microscope, is becoming larger and larger. Most people don't have the computers to load these all into RAM, so you can write it to NWB. So we also provide tools that actually under the hood load the data bit by bit and write it bit by bit. So you can load these in most common systems, like in most computers that postdocs or PhDs or lab technicians will have to do their analysis, like the conversion should work. And as Ben was saying, and I'm gonna just expand a little bit into these, now that we are having all the data in the cloud, the way in which the data is stored internally in this bucket actually matter for the efficiency when some user wants to query the data.
Sure.
The specific layout that we use in the back end is called chunking usually, which you can imagine as how the data is structured into little pieces inside the actual byte. And we also have put a lot of effort into having good heuristics for the most common data, so the access patterns are as efficient as possible. So that's another feature that you win for free with the use of these tools. And we have been thinking, we are still actively thinking about this. Alessio, who is a member of Catholic Neuro as well, has been working on using some specific audio codes to compress some of these signals. Okay, I think I showed you this before, how to aggregate different formats. So that was another example of the same. So let me jump to how to use it. Yeah, I would like to say that we rely on many other open source projects. For example, for extracellular physiology, we rely a lot on the NEO project, of which we contribute a lot to as well, to get access to the data, ROI extractors, which we maintain for optical physiology, and then a bunch of format or manufacturer specific libraries that we use to extract the data. You can install NeuroComp easily like this, and we give the option of installing only the tools that you will need for a specific format that you are transforming. And in a more technical way, we also provide a Dockerized version of the library. All of this is, I would like to reiterate that this is like an open source project. The code is out there. We don't charge anything for using it, and we maintain it as a part of our effort to make conversion to NWB as easy as possible for anyone that wants to access that. So coming back to the question, when will you use the guide and when would you use NeuroComp? So if the format that you want to use is already well known and you are going to transform, I don't know, like 3, 4, 5 sessions, it is very easy for you to use the guide. No need to add more complexity. If you want to transform, for example, we were discussing like you did a lot of recordings, you have a lot of sessions, you want to transform them in one go, yeah, then maybe you should go to NeuroComp because it will allow you to write a short program in Python that gets all the locations of all the sessions, and then you run all of a snippet like the one that I just showed you before. When you will not use it is, I think Ben was mentioning earlier, you may have some metadata that is very specific to what you're doing, some trial information, for example, or epoch, if you have like training period and test period, some quiet or sleeping period, you may need to add that with the low-level tools, which is PyNWB. So let me jump to that. PyNWB and MathNWB, they are the low-level tools that give you access to the specification. They're very well documented, and as we were mentioning before, they can be used to write customized code. So let me show you how that looks. Yeah, one last point is that they're very easy to mix and merge these two approaches. For example, I was mentioning earlier, showing you snippets like this. Oops. So here you will add just PyGLX data with NeuroComp, but then maybe you need to add some specific device that is independent of that, like another camera or something. And here will be the PyNW code that you will use, and then you finish like that. So the two things can be combined. Like you do the easy part with NeuroComp, and then you fine tune or do the last part with PyNW code directly. So let me jump to this actually. Let me give you just show you how the documentation looks like. So that's the main documentation of NWB. You have installation instructions on the top, and probably the part that you should be coming more often if you're working on a conversion is the tutorials. And we have everything. This will be like your basic introduction that shows you how the files are structured, how to access them, how do they look, what the terms mean, etc. And then you have like the main specific tutorials. For example, just a couple of days ago, I was working on doing optogenetics conversion, and I had to remember how certain term was called over there. So I came to the optogenetics tutorial, and they look like this. Okay, let's go to behavioral. So on the tutorial, they'll give you like an introduction to what the objects in NWB are called. Then you'll have code snippets that will take you like step by step to accomplish a certain goal. You create an NW file. You can actually access the HTML of, this is an HTML representation of the file. So for example, at this level, it will only have the general metadata. Then you start adding spatial series to it, which represents gaze, direction, or the position of mice in a maze, for example. And very importantly, we'll take you step by step. And if you're familiar with notebooks, which is a very common tool in analysis, at the end, you can download the whole thing as a script or as a notebook. And the same for all tutorials. So the workflow will be, yeah, you may go through these or these if you want to read, to get acquainted with the format. But if you want to add a specific piece of data that is not covered for Neurocom, then you will go to domain-specific tutorials. If you want to build something advanced, we also have advanced tutorials that will allow you to build tools, for example, to avoid overloading your memory, as I was mentioning earlier, which is a problem when you have this data that is as large as the data in neurosciences. Cool. So we have a similar, the right one. Let me see. Yes, so the same, there is also a general page for documentation of Mat NWB. Over there you have the installation, which in this case will be downloading the library. You add it to your pad in MATLAB. And again, you have like some basic tutorials of how to read Mat NWB, but the complete equivalent tutorials will be there. And it goes from everything. For example, we have as well like behavior, extracellular electrophysiology, intracellular, image data, up to genetics and calcium image. And here I think we even have some like video links that you can see of previous tutorials. So this is the structure of the documentation. Finally, another tool that I would like to talk about is the Dandy CLI, Command Line Interface. So as you were asking earlier, you can use these tools or the guide to create an NW file, and that's used there in your computer. You don't need to upload it. You can store it like that. But if you want to interact with the archive, and you don't do that for the guide, which you can, what would you use to do this in a programmatic way would be to use the Dandy CLI. So that's where this tool enters into the picture. And here's a brief list of features that the Dandy CLI has. So you can download data. Ben was showing you earlier how to download files, either one by one or just with the instruction that the Dandy archive generates for you. But you could use the CLI to just download a complete data set at the same time. You can validate the files just to see if they conform to the standards. It also has a feature for organizing NWBs in the same way that they're organized into the archive. That's the most important probably is that you can upload the data. You can delete Dandy set from there, etc. So here is a brief example of how that would look like. This downloads the data set. First you create the data set, then you download it locally. You start putting files into it, you validate them, and then you upload it. And this is very well documented as well. You can just take a look to that. So yeah, basically here you will find the documentation of the Dandy CLI. Right. The final thing that I would like to talk about is extensions. So Ben was mentioning earlier, we cover in a sense the most classical analyses and type of experiments that are done in neurophysiology. So we have a specific schema for things like subject, behavior, neural activity, etc. But I mean, this is science, so things change, and there is new analysis and new ways of thinking, new modalities of experiments every day. So the format did include a way of extending it so it can cover the needs of the community appropriately. So here are some examples of things that could not be covered. So maybe you are using a probe that you make by yourself, and you might want to source some metadata because you think it is important for the scientists of the future to know this. There may be some pre-processing tool that you are using that you want to store metadata of in some sort of format in the format. And it may be things, for example, I think that when the format started, post estimation was not as automated as it is now. At some point, people realized that they could use deep learning to easily train algorithms for doing post estimation. And now that has become a common tool for many labs. So people create an extension to represent post estimation. That's an example where things entering. So basically, that's the role of extensions. And if your lab has some specific needs, we have also extensive documentation of how to create an extension and the ones that are actually available, because we would like the community to like coalesce around certain projects. For example, the C. elegans community has very specific needs with their experiment. So they have an extension to both represent the imaging data that they do and also the subject. I think that I've been recently told that the subject information that we have in general NWB doesn't apply very well to the C. elegans. I think that specs didn't make sense for them. So they needed new data types to cover for that. And here is an example. We have an extension for sound, an extension for photometry, optical photometry. I think I mentioned post estimation must be there somewhere else. I don't see it actually. Maybe we should add it. Yep, ECOG as well. There is events for TTL pulses, among other things. And we have a complete documentation of how you can get going if you want to create an extension by yourself. So regarding conversion, to summarize, if you want to have your data converted either for your internal use or if you want to publish in the archive, these are the tools that we offer. I think that this diagram is very nice. So you can start with a guide that will be useful for most of the cases. If your experiments are very generic, they use tools that are very standard in the field. You can use NeuroCom if you want to have more programmatic control over your setup. And if you need to do something more specific to your setup, you can access the low-level tools. And if you need to do something that is not even in the format as we have it now, then you will use extensions. So that's all on my side. Thank you very much.
So I have a question, a commentary discussion, I don't know.
Thank you.
So I'm thinking about the way we collect data in the lab. I guess there is a need for mirroring the protocol of experiment. I understand the thing about doing session-based collection, and also because in each session things change. I don't know, perhaps there are chronicle recordings. In our case, most of the times are acute recordings. So in each day, there is a new area to record. There is a new set of conditions where we're measuring the behavior of the monkeys. Also, we're introducing eye tracker or a video for doing movement analysis. Also sounds, etc. Many things that are happening at the same time. Measuring behavior, all that changes on a daily basis. However, we already wrote many codes in MATLAB in order to automatize the way we are collecting the data. So at the end, we collect the electrophysiological recordings and all of that, and we put it together in a simple code in MATLAB in order for us to do the next step of analysis. So, but since I guess all labs have the protocol of experimental, like each day what was done, maybe what the monkey ate, that they had how much reward, so on and so forth. I guess all that list of metadata that is going to be included in the NWB protocol format, is there a mirroring of, let's say, you give me all this metadata list on daily basis. If I'm doing the experiment, I put like this column, all the information, and then in order to put together all the information that is collected from the eye tracker for the electrophysiological recordings, from the position of the electrodes, which many times, most of the times we use like single electrodes because we don't have the money for doing like probes, like it's too expensive for us, right? So we still use like single electrodes, 7 electrodes, 5 electrodes, so on. And we, of course, have these protocols. So the question is, we already have this sort of MATLAB programs, the codes in order to facilitate. So is there a way of mirroring our the protocol, experimental protocol, with whatever is being recorded? Because at the end, it's like doing on session by session. It's like, you know, it takes a lot of time.
Right.
So we solved that already, you know, like.
Right. Yeah, I would say that unfortunately there is not.
Okay.
But I think the important point is that if you really did the work of having an internal standard for organizing your data and for your analysis, you really have like done the most difficult part of this. And even if it is going to be effort, that's going to be like 10% of what you would have done if you didn't have that standard in the first place. Yeah, it is true that, for example, I don't know, let's say like something that we encounter often is MATLAB, for example, has structs inside of it, right? And then you can have annotated columns. And many labs had an internal format of what that means for the typical experimental setup that they have. And they put work into that internal format of theirs to do that. And converting to NWB from that feels like a little bit of duplication. But the good thing is that you will write one script that goes from that MATLAB to NWB, and it will work in all your experiments, right? So I guess I will say no, but I'll emphasize that you are already most of the way there.
So what you're saying is like I can take the structure like from MATLAB and then convert that into okay. Right. Yeah, that's important maybe for me in order to share that, to put it like in the community and the journals and everything, right?
Right.
So that's what I would win in my case. I don't know many cases. I mean, all labs have their own protocols or whatever, right?
Right.
Yeah.
Yeah. Like, so for your own, like if you already solved the internal sharing problem, that's great. And then you can apply 10% of the effort that we have taken to also solve the external sharing problem, which is what NWB will attempt to get you. Oh, that's my take on it. Yes, or somewhere there, I don't know. Oh, I didn't. I probably.
So once you have your NWB data files organized in your lab or uploaded on Dandy, what are the tools that you use to read them?
Yeah, well,
press them to do.
That's a great welcome for the second
okay.
Ben is gonna mention now. Just let me see if they didn't ask anything else on the YouTube. Is there any tools in Eurocomp to read behavioral channels set up as analog input on the same recording system software? So I'm working now on doing that for OpenEFIS. We already did that work for SPY GLX, which sometimes had NIDAC channels. for analog and digital behavior, and the converters take care of that automatically. And we'll be doing in the following weeks the same for open IFIs. So the answer is yes, and we will get more. Okay, I think that's all the questions that we have. So thank you.
All right, I'm gonna, the moment you've all been waiting for, how to actually read and analyze NWB files. We have two tutorials. One of them is in Python, the other one's in MATLAB. I'll start with the MATLAB version since I know a lot of you are MATLAB programmers. So this is linked to in the presentation. I'm just going to download this MAT NWB analysis demo. Okay. Now, obviously, your analysis is going to depend on what type of data you're actually collecting, but I'm going to walk you through an example, simple analysis of one file in NWB. So this is one of the first Dandy sets, and it was contributed by Uli Rutershauser's lab, where they are presenting actual human subjects with images while they're recording electrophysiology, single unit electrophysiology from their brains. So I'm going to, if you want to get this file, I'll show you how to do that. There's a screenshot showing here how to do it, but you would go here. Oops, clicked twice. Okay, and then click Files. And then P11. And then you would download. So I just downloaded this file, and I'm going to copy its path so I have it for later. All right. Now, I don't need to run this step because I already have it installed, but the way you would install MAT NWB is you would do a git clone from this URL, and then simply add the whole directory to your path. So I'm just going to do the path adding part. And then I'm going to, this line here, generate core util.get schema version. I'm going to put the path to the file that I just downloaded. And this will generate a MATLAB API corresponding to the schema that this file used. Now, that's because the schema evolves over time as we realize that as we fix certain issues and add certain capabilities. So once you do that, oh wait, let me change this over. The new path. Okay, so this loads up an object that corresponds to the NWB file, and you can see a lot of the fields here, but this can be a bit difficult to understand. So we have this viewer, this NWB tree viewer. So if you run this, you get this interactive widget that you can use to explore the file. They're directly in MATLAB. So you can look in acquisition and then look at events, and you can see timestamps of certain events. You can look inside of units, and you can see, the different columns in here. We have spike times inside of units. Intervals trials shows you the trials. So you can kind of get a sense for what's in the file. One of the things it has is this stimulus presentation. And if we load that in, we can see, okay, it has a distance of the screen, and then it has data corresponding to the images being shown. So if you do NWB.stimulus presentation, you get the one of those called stimulus presentation, and then you do .data. Now, this is something about reading in NWB that's probably different from what you're used to in MATLAB, which is that for data sets, it doesn't load the data into RAM automatically. Usually when you say load mat, it'll just load the entire file into RAM. We don't do that because often NWB files are so big that you wouldn't want to do that. So what we do is instead you have like pointers to data sets that you can load on demand. So here we have what we call a data stub, which tells you information about that data set, but does not actually load the data set itself. So you can see the number of dimensions and the shape and what the data type is. Now, if you actually want to load data from that data set, all you have to do is index into it. So here I'm taking this object that I returned here, and I'm just indexing in the first 3 of the first dimension and the first 300 of the second dimension, the first 400 of the third dimension, and then 32. That's the 32nd image. And then you get actual data. So that's how you get actual data. If you wanted to load the entire thing, you can do that. You can simply do, if you do this .load, that will actually read the entire data set into memory. But you might all want to do that given the size. Now, this data set was stored in a bit of a strange way, that it wasn't RGB, it was BRG or something. So we have to do a little bit of permutation so that MATLAB can understand how to actually show the image. But once we do, we can take this data, for that's returned from this image object. Okay, this finally returned. So you can see it took a little bit of time to compute, but it did return all the data. I'm going to delete it now because we don't actually want to load all the data. But this image has these raw values. So I'm doing a little bit of manipulation and then actually showing the image. So this each of these images actually is what was presented to the subject. And then you also get the stimulus times. So between the data, which gives you the RGB values, and the times, you have all of the stimulus information you need. And then we need the spike times of the individual units. So you would do nwb.units.getRow gives you all of the data for a given row, which includes the spike times variable, which is 373 by 1. So those are the spike times. It also includes other information about this unit, which we're not going to use, but it may be useful for you. Now I'm going to show you how to create a peristimulus time histogram directly in MATLAB from this data. So we have a few parameters here, which unit we want to look at. We can set that here. I'm using this little fancy widget that MATLAB supports. You could just define this as a variable. How many seconds before and how many seconds after. This is code that we would use to get the spike times from an individual unit. So I'm getting the row that's corresponding to this unit ID, and then I'm getting the column spike times, and then I'm just getting the first element of that cell array. And yeah, so this will change. So this says 1,557. If I change the unit, it'll change to a different length because it's a different unit with a different number of action potentials. Okay, and then once we have that, we want to go through all of the stimulus times and align the spike times to each of those stimulus times, right? So I'm going to create a results cell array. I'm going to take one stimulus time at a time. I'm iterating over the number of stimulus times, taking one stimulus time, taking all of the spikes for a given unit and aligning it to that stimulus time by subtracting it, and then removing all spikes that are less than the amount of time I want to look before, and also removing all of the spikes that are greater than the amount of time that I want to look after. So I'm just left with that window of between 1 and -1 and 3. And then I'm adding that to my results. So that now I have a cell array of spike times where each element of that array is aligned to a stimulus time, and it's just the window I want to look at between 1 second before and 3 seconds after. Now I just need to plot it. So I'm going to create a figure, hold on, iterate over this result cell array that I just created, and then plot each row one at a time corresponding to the action potentials of that unit. I think this will actually look a little better if I do, what is it, like a V line? That work? Not much of a MATLAB programmer, but I think this is right. Nope. AXV line? No, I forget how to make a line here. Is a MATLAB programmer now?
There's just line from where to where you want to go.
Yeah. Okay.
It's X line.
X line.
It's X line?
Yeah.
That's one.
That's what I want. Yep, thank you. Let's make it red. So this shows you when that time of interest is. And so we're looking 1 second before and 3 seconds after. And now that we've set this up, and then here's a histogram, which I think could also use an X line. Okay, so this shows it histogrammed, aggregated over trials. And now that we've set this up as a widget, we can change this unit and then scroll back down and it will re-render this. So here you see a unit that's nicely responsive to the stimulus presentation. And I think there's one around here that interestingly reduced its firing rate. Yep, this one. So this one, I'm always fascinated by these that reduce their firing rate. What's it representing? Who knows? But what I haven't done here is segregate out the stimuli by stimulus category, which is like kind of the next step of this. But hopefully you get the idea. You would then, if you wanted to do that, you could. How would I? Okay, so if you wanted to, you do NWB.intervals trials. Okay, and then I would do to table, which turns this into a MATLAB native table, which is like a little bit easier to work with. And then you can get the category name. Does this work? How do you get that column? I don't think that's right. Well, if
just the number of the
you just do the number?
Like in the parentheses?
You do in parentheses? Okay. Sure, makes sense. So it would be all, comma, 1, 2, 3, 4, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10.
You have a previous parentheses? What is? Yeah.
Oh, I'm trying to do Python-y things. Hold on. There you go. All right, so this is how you would get the category of each of the images. And then you could use that to like refine your analysis script. You can make PSTHs that are specific, grouped by stimulus ID, that kind of thing. Any questions about this kind of workflow of downloading data, reading in the data streams, analyzing them? Okay, I want to quickly go over how to do this in Python, because in Python, we have the extra ability to stream data, which I think is really important. Let's go back to here. Okay, so I'm walking first through installation steps. If you're a Python programmer, pip is the most standard way of installing things. So pip install, and then you can just list the libraries you want. Dandy, PyNWB, remfile, matplotlib are the ones I'm going to use here. This will find these libraries on PyPy, the standard package repository, download them and install them automatically into your environment. I already have all of that, but I will just show you how you will install these things. I'm just going to check that remfile is installed, and it looks like it is, so I'm fine. So in Python, any class or function that you want to use, you have to import first. So this is just a big import statement where we're going to import all the tools that we're going to use. And then this, goes through downloading the data in exactly the same way. There's also programmatic tools. If you have the Dandy API, you could do Dandy download and just download the entire thing. Or you can download assets corresponding to a specific subject like this, or like this, or you could download a specific asset, a specific NWB file. Dandy download is quite flexible. You can download different levels depending on what you need. We're just going to do, and then there's a third way, which is using the API. So here you can specify the Dandy set ID, the relative path of the session you want, and then use the API to get that object and download it. We've already downloaded it, so I don't really need to do any of that. So I'm going to read this file in and then produce this NWB file object. One thing that we're able to do in Python, which is really nice, as Alberto mentioned before, we have this interactive rendering of the file itself. So here is a representation of the file, and you can drill in and actually view a lot of the data sources directly from here interactively. So here's the trials table, for instance. We have also a way of reading this file using a context. It's a bit more advanced. All of your code to access the file content should be like within this indent, and then it's not accessible outside. This is, I don't recommend this for interactive programming, but once you have something set up, this is technically better because it automatically closes all the files once you're finished using them. But anyway, whichever way you want to load the file, here's how you would do nwb.subject. You can see information about the subject. NWB file.stimulus. You can see information about the stimulus. You can see this is a dictionary with a single key, so we're going to use that. And here you can actually see the data corresponding to the stimulus presentation. Here, just like in MATLAB, we're not reading all of the values of the data. We're just creating a pointer to the data set. So this just gives you information about that data set. Same with timestamps. We haven't actually loaded them. You can see that here. There's an HDF5 data set. If you want to actually access the data here, you would use this syntax to say just load, it's an index, but it indexes everything. And then that will load this multi-dimensional array of all of the stimuli that are shown. And that shape is 200 by 400 by 300 by 3. So this is the RGB part. And there are 200 images shown that are 400 by 300 pixels. Now, again, we have a bit of code to take one of the images, reorder the variable so that it's RGB, and then use plt.imshow to show one of the images. So this shows, you can just change this number and you get what image was shown. Then we've got the units table, which stores all of the information about the spike times. This can be converted to a data frame, which is a common type of table in Python. You can do all of your data frame operations from this if you want, if that's more convenient for you. You can get spike times like this. So you just do units, the data frame that you've created, spike times is the column that you want, and then this is just the, so Python indexes by 0, not 1. So this is like the first unit in the table. So you can change this around, you'll get different values. And And again, I want to just show basically the same thing where you would use Python to create this peristimulus time histogram. So specifying 1 second before, 3 seconds after. You want to get the timestamps from the stimulus presentations. Here, I'm going to iterate over 3 different units. For each unit, I'm going to get the spike times for that specific unit. And then I'm going to start to create a list which holds the spike times corresponding to individual trials aligned to those stimulus times. So aligned spikes, we get the unit spike times, and we subtract the time of the stimulus, because we're iterating over all these stimulus times. And then we're going to chop off anything that's less than -1 and anything that's greater than 3 and append it to our list of results. So this is very similar to creating a cell array in MATLAB. It's just using slightly different syntax. We're using a list instead of a cell array, but it's more or less the same thing. And then this does it for 3 different units. So here is the result of that. Then the plotting function, there's this nice little plot called event plot, which is like perfect for rasters. And then a bit of axis labeling. And here, okay, here's unit 0, unit 1, unit 2, and how they respond to the stimulus. Again, you might want to access trials. So here's the data frame. And if you wanted to, look at the images corresponding to like a specific category name, then you can sub-select this trials data frame by a certain category name. So I'm going to say I only want to look at landscape stimuli. So I'm going to find the rows where the category name equals landscapes, and then I'm going to find the data corresponding to those rows and plot it. So here you can see all of the first 3 images that are categorized as landscapes. So you can change this around. Let's say one of the categories is phones. So you can do that. And you'll get all the phones. Okay, so you can kind of see how you go from this to doing something specific about like maybe nature photos versus physical object photos, and then having some kind of hypotheses about certain neurons and how they tune. I wanted to go more on the technical side for a second, because there's this capability of streaming data that I think is really important. So in both of these previous examples, both in MATLAB and in Python, I was showing you're downloading the data and then you're reading it locally from your computer. But actually, I often recommend another approach to accessing the data, which is streaming the data directly from the archive. And essentially what you do here is you create an object that looks exactly the same as if you were reading it from your computer, but every time you read, anytime you would have done a disk read, instead you're performing a fetch of data from the S3 bucket. So it's as if it were on your computer, but every time you would be reading from your computer, instead you're reading from the internet. And that sounds complicated, but it's actually really easy to set up. So the first thing you would need to do is get the S3 URL of the asset that you actually are interested in, right? So there's a simple way to do that. So you've got the Dandy set ID and the file path, and then in just a few lines, you can get this S3 URL. So you would just copy and paste this code. And then this is the URL of this NWB file stored on the Dandy archive. So if I take this and I copy it into my browser, I get the ability to download it. But because this is just simply a file, right, that's stored on S3. But I'm not going to download it. I'm just going to take this URL, and I'm going to use a library called rem file, which stands for remote file. And I'm going to basically put in this S3 URL and say, create a remote file where you're finding the data at this URL. And then I can create this NWB object. I'm creating this remote file. I'm opening it in H5Py, which reads HDF5 files. And then I'm reading that within this NWB specific reader. It's a bit convoluted, but at the end of the day, you can just copy and paste this code. At the end of the day, you get this NWB file object. And if you actually look at this, it looks exactly the same as the object that we had when we were reading the file locally. But this isn't reading the file locally. This is reading a remote file. So all of this is being streamed on the fly as we request it, and it's really quite fast. So, so here we have this NWB file stream, and we can do the exact same code as we did before. And basically what's happening here is when you're making this call to read a specific range of data from the NWB file, instead of reading it locally on disk, behind the scenes, it's automatically reading it from that S3 bucket. But the really cool thing about this is you only are ever reading the data that you need. It's not downloading the entire file. So you can have a 100 gigabyte file, and we do have over 100 gigabyte NWB files on the archive. And if you want to just read one image, all you're downloading is that image. You don't have to worry about the fact that it has all this raw data that's making it really big. Yeah, and so then you could just take this NWB file stream object and do exactly the same analysis as you did above, and it'll work exactly the same way. And then here's how you close it.
You can do this same type of thing without accessing, you know, from the cloud.
Yeah, I mean,
you can do that from your own computer. I mean, you have 1,000 NWB, you know, files.
Yeah.
And you want to specifically look at one stimulus condition and all the spikes of all the neurons recorded.
Mm-hmm.
You will be able to access that with a similar tool, right?
Yeah. So I mean, so are you talking about files that are locally on your computer, or?
Yeah.
I mean, then you just wouldn't do the streaming thing.
No, I know. It's not streaming, but
right. But that, I mean, you would really have to write your own code. Okay, or do a for loop over all of the files, read in the data that you want to read in. We want to provide automated analysis tools, but to be honest with you, once you get into aggregating over multiple sessions, it becomes very custom and very experiment specific. So it's really hard to build tools that aggregate over multiple.
Right. I understand.
Yeah.
But probably you already have some, you know, general.
Yeah. I mean, one thing I would do is say, look at the Jupyter notebooks that are posted on Dandy Hub already, because several of those do that kind of thing where they're iterating over multiple sessions. But really, it would literally just be like a for loop over sessions. You write a little bit of code to get the specific element of the specific data stream that you want, right? And then you put that into a container that's aggregating all of this data. You know, it's the kind of thing, hopefully it would take you less than a day to put something like that together.
Right. That's right.
All right. So that's the interactive read tutorial in MATLAB and Python. That's basically everything we wanted to show you guys. Is there any questions about anything we showed in this afternoon session?
I guess more questions are going to be
more
session.
Yeah, Alberto, any questions in the chat? Okay, so the plan is tomorrow at 10, we will be in this other room.
The other building.
Right.
Your science building. The round table.
Great. Yeah. So we'll be there. We would love to, you know, learn about your specific data problems, whether it's reading data already on the archive or converting your own data, publishing. You know, we're here to help. We've kind of blocked off tomorrow to work with you. And yeah, we'd love to see you guys there.
Bravo.
Oh, yeah.